RL circuits C. So there's the problem. If you want to try this on your own, please stop the video and then you can start it whenever you feel like you want to check your answers. So what do we have here? At time equals 0, we're going to close this switch here. We have a bunch of circuit elements in series, including an inductor, which means that at that first instant, we're not going to have any current going through this 1 ohm resistor. We're not going to have any current going through the 3 ohm resistor. We're not going to have any current going through the 4 ohm resistor. Because there's no current going through any of the resistors, there's not going to be any voltage drop across them. The inductor is going to be fighting our 32 volt battery just at that first instant with 32 volts. And which way is that inductor's EMF acting? Well, according to the picture, it's going to be fighting the battery. So I think that one right there. All right, that was pretty easy. What about at time equals infinity? Well, at time equals infinity, the inductor, let's start right there. The inductor just acts like a wire. So there's that. And if we want to circle our correct answer down here in the lower right, inductor is not going to be doing anything at time equals infinity because the current isn't going to be changing, and the inductor, you might say, just falls asleep. Which means at time equals infinity, we have a total of, how much is this? 8 ohms of resistance, 3 plus 1 plus 4. We have a 32 volt battery. So the current going through the 1 ohm resistor is going to be 4 amps. The current going through the 3 ohm resistor is 4 amps. The current going through the 4 ohm resistor is 4 amps. What about the voltage drop? Voltage is I times R. The I is 4 and the R is 1. That's going to be 4 volts. I times R here, 12 volts. I times R here, 16 volts. Let's check and make sure that that is, in fact, our 32 volts. It sure is, isn't it? 4 plus 12 plus 16. We have dropped our 32 volts that we need to as we go one time around the circuit.